My name is Seungwhan Baek, and I work at the Korea Aerospace Research Institute. Thank you for inviting me to this seminar. It's currently about almost 11 a.m. on Sunday in Korea, and I believe it is evening in United States. I hope this seminar makes for enjoyable evening. This presentation covers various heat transfer issues in launch vehicles using cryogenic propellants. I will discuss the historical background, the challenges we encountered during the development of KSLV-2, which is Nuri rocket, and outline our future work. As the master introduced briefly myself, I completed my bachelor's, master's, and Ph.D. in mechanical engineering at KAIST in Daejeon. I spent 2 years as a postdoc researcher, a guest researcher at NIST in the United States. The research I conducted there is currently published on the NIST website, where I work on the fundamental heat transfer coefficient measurements. Recently, I also published a recent paper on cryogenic two-phase heat transfer, so I would appreciate your interest in my work. The use of cryogenic fluids in launch vehicles began with the start of the space race. Even before the Saturn project, which aimed for the moon, and the liquid hydrogen and liquid oxygen were used in upper stage of this Atlas Centaur rocket, which is specifically in the Centaur's upper stage. This made it in a typical cryogenic launch vehicle to utilize such a cryogenic liquids. It was necessary to develop a thin-walled propellant tanks. For example, efforts were made to store cryogenic propellants in structure as thin as beer cans or PET bottles. But consider this, when cryogenic fluids absorb heat from the outside, they evaporate. If evaporation continues, these thin-walled beer cans or PET bottles will, without proper pressure management, will eventually burst, like in this video. As the early launch vehicles, Atlas Centaur, we experienced similar challenges. On the ground or during the acceleration, cryogenic fluids exhibit phase separations where the liquid and gas separates. In this situation, predicting pressure increase is relatively straightforward. Now, let me introduce another key concept, microgravity. I will briefly explain how cryogenic fluids behave in microgravity. In the absence of external forces or disturbance, the fluid will climb the wall along the tank walls. This happens because as gravity weakens, surface tensions becomes the dominant force. However, if cryogenic fluids climbs the wall, another phenomenon comes into play, which is heat transfer, boiling. This occurs due to the temperature difference, just like when a beer can is warm while the beer inside is cold. Eventually, the beer comes warm. This leads to unexpected situations. Managing cryogenic liquids in microgravity presents many unpredictable challenges that are difficult to anticipate under normal gravity conditions. In the 1960s, NASA researchers strived to predict as many unforeseen problems as possible, ultimately achieving the historic milestone of sending humans to the moon. I believe that understanding how cryogenic fluids behave in microgravity and identifying the phenomena that disrupt their movement were crucial tasks for NASA's success. The KSLV-2 Nuri rocket, which has been launched in Korea recently, follows the same principles. Its first launch took place on October 21st, 2021. Nuri is also a cryogenic launch vehicle using liquid oxygen as an oxidizer and kerosene as a fuel. The Nuri rocket also contains many hidden challenges related to cryogenics. One example is the engine cooling before ignition. As liquid oxygen travels from the tank to engine, uh, and through the pipings, the engine itself is relatively hot, and this causes boiling, which can lead the flow oscillations during ignition, potentially disrupting the engine startup. To address this, the engine piping must be cooled before. This is done by establishing a natural circulation loop, which helps to resolve the issues. At first, I also didn't fully understand why this circulation occurs. Uh, as you can see in this video, this is not some kind of magic faucet like this. This circulation process driven by temperature difference. The principle is relatively simple. The hot fluid rises and the cold fluid sinks. By leveraging this natural behavior, the circulation loop is created. Uh, we designed a simple experimental setup to observe the circulation of liquid oxygen and then apply these findings to launch vehicle design. In mathematical terms, the circulation loop is modeled by ensuring that the net fluid pressure drop around the circuit is zero. We organized this analysis and published it in a paper. The main focus is on determining the flow rate in the circulation loop and evaluating the cooling performance by considering that cold fluid sinks while the fluid heated by external source rises. Let me share some additional details regarding the development of the Nuri rocket, KSLV-2. In order to use liquid propellant in Nuri's rocket tanks, the tank must be pressurized. Typically, helium is stored under high pressure in a cryogenic tank and gradually drawn upon for use. However, since the storage volume in a cryogenic tank is limited, the volume must be expanded as much as possible during the pressurization. To achieve this, the heat source from engine is utilized. In other words, heat exchanger is employed. By assessing the performance of heat exchanger, we can predict how the tank pressurization will occur and estimate the amount of helium required. Various tests have been conducted to understand these relationships. To evaluate the standalone performance of heat exchanger, several large-scale experiments were conducted. In these experiments, room temperature helium was cooled down to cryogenic temperatures, and the heat exchanger performance was assessed under conditions very closely resembling the actual environment. After the heat exchanger was assembled to the engine, we verified the actual performance of the entire engine assembled and proceed with Nuri's launch. Up to that point, everything went smoothly. However, the first launch of Nuri rocket was not smooth as anticipated. Problem arose in the third stage, where the engine shut down prematurely, leading to a failure to reach orbit. Upon investigating the failure, we discovered that helium tank, as mentioned earlier, had become dislodged from its proper positions. Typically, one might expect forces acting opposition to the direction of travel to press tank downward. However, that was not the case. Just as balloon in a bathtub of water tends to float upward, a similar phenomenon occurred with Nuri's rocket. During the acceleration, the helium tank filled with a lighter gas attempted to rise during the acceleration. Uh, so this upward movement caused the helium tank to puncture upper part of the oxidizer tank, ultimately resulting in a leak of liquid hydrogen. When Nuri rocket separates its satellite, it experiences a microgravity environment. Due to the reason I mentioned earlier, the liquid oxygen was leaking, and many people couldn't understand why the liquid oxygen would leak from the top of the tank in microgravity environment. I didn't understand it either, so we conducted several experiments to investigate why this happens. The most challenging part was creating a microgravity environment. So we built a small drop tower to simulate microgravity conditions. After successfully creating a microgravity environment, we observed the movement of the liquid. We set up a small liquid chamber and installed a camera to compare behavior of boiling versus non-boiling liquids. In this video, you can observe the behavior of liquid under both boiling and non-boiling conditions. When not boiling, just like water, the liquid predictably climbs the wall. It is quite predictable. However, when boiling, the liquid ascends the walls unpredictably and even faster than in non-boiling cases. When we shared these findings, many people were convinced by the results. Mm. So now KSLV-3, the next generation launch vehicle, is aiming to incorporate a reignition capability. Many American launch vehicles already have this feature, but ours does not. Ours do not. To make reignition possible, we must understand the behavior of liquid in microgravity. In other words, Korea must have the ability to create microgravity environments and conduct cryogenic liquid experiments. To create microgravity environment, we have made efforts to build a drop tower capable of achieving drop times comparable to those in United States and Germany. By utilizing an existing tower facility, we are now conducting drop tests to generate microgravity conditions. While facilities in the US and Germany can provide microgravity about 5 to 10 seconds, we have established an environment that can achieve approximately 4.7 seconds of microgravity. This video is the part of the drop test footage. We observed the drop capsules descending in a straight line over a distance of 120 meters. I vividly recall staying up late until the morning to ensure it fell straight. The 60 kilogram weight drop capsule successfully fell 120 meters, securing approximately 4.7 seconds of microgravity. In fact, we received significant assistance in setting up the drop tower. We now have the drop tower network with Germany's JARM and the US NASA Glenn Research Center. And we've received a great deal of expert advices. Currently, and in the future, our research is focused on a mechanism that passively controls liquid behavior in microgravity environment. One such mechanism is that microgravity liquid acquisition device. You can see in this video how the liquid behavior changes depending on whether this device is present. Because the behavior of liquid can be controlled by mechanical devices, enhancing the utility of liquids in microgravity will play a major role in cryogenic launch vehicles operating in microgravity environments. The key is to design a liquid acquisition device to serve as the engine inlet, ensuring that only liquid flows into the engine. NASA and Elon Musk are currently aiming to achieve human missions to Mars. A trip to Mars cannot be accomplished all at once. In orbit, refueling is essential. For instance, in the case of a Starship, liquid methane and liquid oxygen needs to be replenished. Just as your car stops at a gas station when it runs out of fuel, spacecraft will need to refuel at space-based refueling station. The challenge, however, is that this fuel is a cryogenic propellant. In gravitational environment, room temperature fluids naturally separates into liquid and gas, so transferring them isn't particularly challenging. However, when refueling cryogenic liquids at a microgravity orbital refueling station, as explained earlier, the overlapping issues of liquid transfer and heat transfer arises, creating many factors to consider. Currently, the research is underway to address the transportation cryogenic fluids in microgravity. The United States is already ahead. Intuitive Machines Nova C has reached the moon using cryogenic methane and oxygen. They managed to regulate the storage of these propellants in a thin beer can-like containers, keeping them from rupturing over the course of about a week until they arrived at the moon. Cryogenic fluid management is a research area that has garnered a significant interest at NASA. In microgravity, accurate mass measurement, pressure management, and temperature control will be crucial technology for the missions to Mars. We are committed to collaborating and researching these topics so that humanity can one day journey to Mars, as well as KSLV-3. So that's all I have prepared. Thank you for listening my presentations. Thank you.